Let's start off with a little bit of an introduction to chemistry. Just kind of what is chemistry? There's a few branches to chemistry. What does it mean to start thinking like a chemist does? So let's just look at a little bit of an introduction here. So first thing to think about is, what are chemicals? Well, chemicals are everywhere. Everything that's made up of elements from the periodic table is a chemical. So everything from the worst, most poisonous substance out there is a chemical to things that we eat all the time. It's all chemicals. Nothing that you can touch or hold is not made of chemicals. And that's something to consider. There's a lot of very interesting scare stuff that goes around online where people say, oh, this is one chemical away from this terrible substance. Okay, so it's slightly different, but very similar. Doesn't mean it's anywhere close to the same thing. As we study chemistry, hopefully you'll start to understand that everything is its own unique substance. We start off with reactants. Okay, I have two different substances. I react them. I make products. My products have completely different chemical properties from my reactants. So everything's a chemical. Looking at a typical kitchen, you can see some examples here. If you have glass, that's silicon dioxide. Our water, depending on where you are in town, will have slightly different treatments. And one of the things that we'll look at this semester is water quality reports and how do we interpret those and what do all those numbers mean? Okay. The refrigerator in this picture is made up of a metal alloy. If you have a gas burning stove, you have natural gas coming in. If you have produce that you have purchased from the store, there's going to be fertilizers and pesticides and stuff on them. Like whenever I get fruit home, I always wash it because there's always something on it. It's actually interesting. If I have to buy an orange versus if I get an orange off the tree in my backyard, there's always a residue on the oranges that I purchase in the store. My husband, he really likes a drink called an old fashioned. And an old fashioned, you need a little bit of an orange peel for the drink. And it's much harder to get a good orange peel off of an orange we purchase from the store than the ones that we get from the tree, because the ones purchased from the store have been treated with stuff. So everything has chemicals. All right, so what is chemistry? Basically, it's the science of the properties, composition, and behavior of materials. We want to describe the different forms of matter and the chemical reactions thereof. So we look at all sorts of different things in chemistry. In fact, there are a bunch of different branches of chemistry. We have applied chemistry. That's usually what you're going to see more in a commercial setting, where you're looking for and trying to isolate useful materials. And then theoretical chemistry, where we want to just explain things because we want a better understanding of the world, or we just think something's cool. A lot of academic research is in theoretical chemistry. And then there's 5 main branches under that: inorganic, organic, physical, biochem, and analytical. I was trained as an analytical chemist, specifically an electro-analytical chemist. I did work with what we call redox-dependent hydrogen bonding. I know, probably doesn't make any sense at all, but redox has to do with the state that something's in, and then hydrogen bonding is a type of interaction that we get between molecules. And so I was looking at that particular type of interaction based on the state that something was in. Very useful for molecular recognition, like having on-off switches at the molecular level, or looking at sensor technology. If you know anybody that has to test their blood for blood sugar for diabetes or something, that is an electrochemical sensor. And so I worked with understanding those types of processes. All right. So inorganic looks at elements, properties, preparation, applications of compounds. Organic, living things, carbon in its compounds. Physical chem, very theoretical, very math-based, lots of crossover to physics. Has some interesting stuff, but that was probably, when I was in school, that was the one that gave me the most challenge, was physical chem. I like math. I don't like solving triple integrals. Biochem looks at obviously living systems, and then analytical chem looks to study constituents, identify things in chemical processes. One of the cool things about analytical chem too is a lot of times we're trying to do things that maybe haven't been done before, and so we kind of have to do these weird like Frankenstein setups where we're trying to build a new way of analyzing something. And so there's a lot of really cool hands-on, craziness that goes on trying to develop some of these techniques. When I was doing research, my PI and I, we were looking at this one system, and we realized that we not only needed to do our normal scans on them, but we needed to have another piece of information. And so one of the things that I did in graduate school was I had to develop a technique to run two different types of analysis at the same time. I had to build my own little sample vessel, and it went through a lot of different iterations as I was building it. And I had to have both machines running at the exact same time. And I had to have the sample vessel capable of giving me the data from one machine and the data for the other machine at the same time. It was really crazy, but it was a lot of fun. I really, really enjoyed getting to do that type of work. So, it's no surprise that I still have a, shelf full of Arduino boards and other circuitry and stuff that I still like, fiddling with when I have time. All right. Talk to anybody that does something and they're going to be a little bit like, well, what I do is, the most important thing. So we can be a little egotistical sometimes with our tunnel vision. So we like to say that chemistry is the central science. And in fact, when we look at all sorts of different branches of science, there's a lot of ties into chemistry. If you think about the medical field, tons of ties to chemistry. We wouldn't have any of our pharmaceuticals if we didn't have chemistry. Nutrition, the way all that stuff interacts in our body, all chemistry. And if you start hearing about things like where people that deal with high blood pressure, they need to adopt a low sodium diet because sodium, will do things in your body that's both necessary and undesirable. So even on a low sodium diet, you can't completely cut out sodium because there's some important processes that require both sodium and potassium ions in your body. And so that's all chemistry. Biology, there's a lot of chemistry there. Biochem, chemistry's in the word for biochemistry. Physics, environmental science. We're going to talk a lot about the environmental stuff in this course, where we're going to look at how chemistry ties into ecology, pollution. In fact, in the first chapter, when we talk about what's going on with our cell phones and all the different elements that go into making a cell phone, one of the things we're going to discuss is what do we do with these devices when we're done with them? Some of the elements that we use to make components of our cell phones are present in trace amounts, or they're really, really hard to get. And so what do we do? Do we just start chucking them in the landfill? Can we recycle them? Can we recover anything from them? So that's really important. And then we're also going to talk this semester about climate change and what's happening to our atmosphere as we release things into the atmosphere. In fact, it's kind of interesting. When fossil fuels and stuff were being burned and we started releasing all sorts of carbon dioxide into the air, a really, really long time ago, like over 100 years ago, people started doing calculations to figure out, well, what are we doing to our planet if we release all this carbon dioxide into the air? And they figured out over 100 years ago what we're seeing today. And their calculations are pretty good compared to what we're seeing today too, about how much we're going to be heating up the atmosphere and everything. So we're going to look at that. We'll also look at water. Okay, why is water so important? And if we're not careful, what are we doing to our water supply? So lots and lots and lots of stuff that ties into that environmental impact that we have on the world. Plant science, a lot of chemistry there. So One thing, if you ever grow your own stuff at home, be it flowers, vegetables, fruit, the pH, so the acid balance of your soil is really important. When we first planted our lime tree, it did not produce for well, and that's not unusual. Sometimes it does take fruit trees to quite a while, several seasons before they actually start producing. But one of the things that we were looking at, because by our third season we thought we would see something, and so I started doing some research and trying to understand a little bit better about, well, okay, when would we start seeing fruit production, because our lemon tree produced really well. And it turns out that lime trees, there are things that you can do to the soil to adjust the pH balance, not just the nutrient level in the soil, but the pH balance as well, to have a better possibility of yielding fruit. So I, did some stuff with the soil, and today we've got a very, very prolifically producing lime tree. There's flowers that the color of the flower depends on the pH of the soil. So if you alter the pH, you might get one color flower versus another color flower. So there's a lot of that that goes into it as well. Astronomy, when we look at our galaxy and the universe and everything, there's chemistry there. We can use spectroscopic techniques to figure out, oh, there is, this gas and this gas and this gas around this extrasolar planet. Geology. Okay, when we talk about, hey, where do we get some of these elements from? Well, some of those we have to mine out of rocks. And it's not always a simple matter of we have a vein of a certain element that we can just get in its pure form. Sometimes we have to mine ore, and then we have to process that ore in order to get out the actual element that we are looking for. And so there's a lot that goes into geology. So chemistry, it ties into everything around us. As we talk about chemistry, we'll start to understand different ways that we represent the substances around us. So we have our macroscopic view, which is what we can see with our naked eye. So when I think about water, okay, so water has this chemical symbol or chemical formula of H2O. So we have our hydrogen, which is the H, the oxygen, which is the O, and then the subscript 2 next to the hydrogen means that there's two hydrogens, all right? So I can't see individual water molecules, but if I take water and I heat it up, I can see the bubbles forming as I start to vaporize the water and change it from a liquid to a gas. Okay, now the particulate view, this right here, okay, the H2O there. So we have colors that we use to represent atoms when we are putting things together in these, ball and stick or space filling models. And so little red pieces usually represent our oxygen. Little white pieces usually represent hydrogen. So I can actually take some pieces here, and I can put together a little model that allows me to kind of represent what water looks like. This is not my favorite model kit, but it's the one that was sitting closest to my desk. But the other thing too is on the oxygen, there's also some more electrons. So this is a little bit better view there. Okay, and so we have our particulate representation. So I can either draw something like that, or I can put together a physical model that helps me visualize that. The other thing I can do is I can draw, to help imagine the particulate level, what is called a Lewis structure. Okay, so that's what the Lewis structure for water looks like. And then we have our symbolic view down here, okay, which is where in this situation we're not doing a whole lot. We're just taking liquid water and turning it to gaseous water. Now in this bottom view, we've actually written out the word liquid and written out the word gas, but normally we like to shorthand everything. So if I were writing this out, I would write it H2O and then an L for liquid. And then I would put a triangle above my arrow to represent that I'm heating it. And then I'd have H2O, yeah, so that is a chemical equation showing this is what's occurring in this process. Okay. Now, as we start to delve into chemistry and as we start to understand what it means to think like a chemist, this is a picture I took several years ago when I was sitting at, I think it was La Jolla Shores. My dad was sitting behind me, strumming his guitar. I was home visiting from UC Davis. It was when I was in grad school. And it was just a nice, beautiful day in San Diego. But I got to thinking, when my dad stopped playing his guitar, we started talking about just what we were looking at. And my dad, he's not a scientist. He's not a chemist. He's a designer and a musician. And so when he looks at the scene, he sees more of just what's in front of you. There's a squirrel that's eating an ice plant. There's a beautiful ocean. It's obvious that the sun is shining. Just very chill, peaceful day. But my brain works a little different. I am a scientist. I am a chemist. And when I look at scenes like this, I start to think, well, is that salt water? Is that fresh water? What's dissolved in there? What sort of minerals are in that water? Is that water clean or not? Which especially is important here right now in San Diego when we think about the rains that we've been having and the fact that it's not safe to go in the ocean right after it rains because there's all the runoff from our streets and then all of the pollution that comes up from other areas from sewage plants. And so as a chemist, even though I don't necessarily always work with the ocean or anything, I still think, well, what is in that water and what else is there? When I look at the sand, same thing. Okay, is that pure sand? Is there something else there? Is that just silicon dioxide? Is there something else that, is in that sand? When I look at the squirrel and the ice plant, my brain starts to think, okay, what sort of nutrients is that squirrel getting from the ice plant? What is in ice plant that feeds the squirrel enough that that's going to give the squirrel fuel to keep going? So hopefully, as we go through the semester, you won't necessarily obviously turn completely into a chemist, which would be really cool if you did. But hopefully I can inspire you to start probing a little deeper, looking a little bit underneath the surface at what you see in the world around you and start questioning, well, is that water clean? Is that water dirty? Is that fresh water? Is that salt water? So on and so forth. As scientists, we employ the scientific method. And so we think about, all right, we've got empirical facts. We've got these observations. We have our scientific laws we've tested. As we start to formulate understanding of a problem, we can create a hypothesis, which is, essentially an educated guess. And the key there, though, is educated. I don't just blindly throw out something like I don't know, here's a practical example. I drive to campus and there's a ton of cars in the parking lot. I can propose a hypothesis based on facts I know. If I'm driving to campus and there's a ton of cars in all the parking structures and it is week 1 of classes, my hypothesis based on the observations I have made, lots of cars, week 1 of classes, my hypothesis could be that all the students have come to campus either to attend class or try to crash classes. And then what I can do is I can design an experiment to test that. I can go around to different people on campus. Hi, why are you here today? Hi, why are you here today? And I can either prove or disprove my hypothesis. Maybe everybody says, yeah, I'm here because my classes just started today. Or maybe everybody tells me, yeah, no, I'm here because there's a really cool guest speaker that's going to be in the performing arts building. Okay, so sometimes our hypothesis is correct, sometimes it isn't. And so as we go through this whole thing, unfortunately, I'm still getting used to this new method that I'm using to record lecture videos. So I'm covering up the part of this diagram that says reject hypothesis. If you pull the slides before you watch the videos, the whole picture will be there because my face won't be there. But basically, as we go through, it's an iterative process. When we make our observations, we make our hypothesis. We predict what we might see, then we design these tests, our experiments, and then we do them. If we support our hypothesis, we still do further tests because maybe it's a one-off. Everything needs to be statistically significant. And so a single experiment is not going to be statistically significant. I have to do things more than once in order to get that significance. And so sometimes it's supported. Great. I do more tests. I get more data. I run my analysis. Now I can publish something or tell the world. Other times, though, I go do my tests and, well, yeah, that just didn't work the way I thought it was going to work. And so I have to reject my hypothesis. And then based on the information I have gathered from those original tests and my original hypothesis not working, along with my original observations, now I can make a new hypothesis. And a lot of times we learn more when our original hypothesis doesn't work and we have to kind of, broaden our horizons and think outside the box a little bit more. Okay, so some important terms, hypothesis. Okay, again, keep in mind, very important word here, educated guess. Okay, when we make a hypothesis, yes, we are guessing at something, but we are doing so in an educated fashion. We're taking information we have to make a hypothesis. Okay, so we're not just gonna blindly throw out random stuff. It has to be a guess based on information we've gathered. Okay? If we have enough evidence for things, we can put together theories, unifying principles that explains a whole group of facts. Okay? If we have a set of tested hypotheses that gives the overall explanation of some parts of nature. It tells us why things happen. Then we have our laws. So concise verbal or mathematical statements of a relation that's always the same under the same identical conditions. So no matter what we do, we will always get back to that same thing. So there's something called the law of constant composition, meaning that something like water, it doesn't matter where I find it, it's always going to be H2O. We're never going to deviate from that. If it's not H2O, it's not water. Okay? And so we get these summaries of our observed behaviors. Okay, so let's think about the scientific method. So, okay, think to yourself, what part of the scientific method might this be? I cannot wake up to get to my Friday morning class at 8 a.m., even though I really want to be there, right? We all love Friday morning 8 a.m. classes. So what part of the scientific method is that? Ask yourself, and then let's see if you're correct. Observation, okay? Now, if I set my alarm, I will wake up and make it to class. Okay, so think about that for a second. What part of the scientific method might that be? Hypothesis, okay? It's an idea that proposes that explanation. So, okay, next Friday, I try this, but after turning off the alarm, I fall back asleep. Okay, what part of the scientific method is this? It's an experiment. Okay, so you're like, okay, here's my hypothesis. If I set this alarm, I'm going to wake up, I'm going to get to class, it's going to be fantastic. So the next week you try it, turn off the alarm though, and you fall back asleep. Okay, so that didn't work. If I move my alarm clock across the room, I'll have to get out of bed to shut it off. What part is this? It's a reiterative process. So this is your new hypothesis. So your original one failed, so you had to create a new hypothesis. Okay? Following Friday, you make it to class for an exciting discussion. New experiment, new observations. All right? So this is what we do as scientists, is we go through all of these different things. Okay? And then you don't have to memorize this. This is just factoid, interesting information. If we start looking at this, here we have 1687, 1774, and then we have a bunch of stuff in the 1800s, and then a whole bunch of stuff in the 1900s, and then now the 2000s and beyond. And so, we started off slow, and then as our understanding of the world as a species grew and our technology grew, we were able to do more and more and more. And so, we started off small and small and small, and then boom, now we've got all these discoveries. And it's really important to start to learn how to discern what's good information from what's bad information as we start putting together some of this stuff. Like this really trips me out when I look at this, okay? This one I think is really important to mention, this polio vaccine, okay? Um, there we go. Jonas Salk developed that polio vaccine in 1954. So polio was really frightening. In fact, there's a dude that just died recently that got polio in the 50s and lived in an iron lung the rest of his life, and he was paralyzed and everything. It was really crazy. But this was revolutionary when this came out, because now all of a sudden parents didn't have to fear that their kids were going to catch polio and either die or be paralyzed or confined to an iron lung for the rest of their lives. People lined up at school to get this vaccine so that they were not afraid of this disease anymore. But then here we are, 2024. Okay, 70 years later, and we have people that are starting to go, oh, well, maybe vaccines are not good because we never see these diseases anymore. So why would we get vaccinated? We get vaccinated so that they don't come back. In places where there's a lot of people that don't want to get vaccinated, now we're starting to see rises of these diseases again. So they're not eradicated, they're just mostly eradicated because we've done the responsible thing by trusting the science that's been around for a long time and getting those vaccines. And of course, not everything, there's nothing out there that's not without some level of risk, but it's one of those where the level of risk is so small compared to the benefit therein of it. So, all right, so that's just a little introduction, overview to chemistry, and kind of how we start interacting with the world and thinking like a scientist does.